visible?
Yeah.
Okay, so the paper which I have selected is for the hierarchy of coherent structures and real space energy transfer in turbulent channel flow. And
Okay.
so the introduction in this paper, the author basically what the author has done is he's analyzed the fully developed turbulent channel flow at the frictional Reynolds number at 4179 and investigated the self-sustaining mechanism of the hierarchy of coherent structures in the turbulence. It all started when in 1995, Hamilton, Kim, and Waleff studied and observed the streamwise vortices induced in low and high speed streaks by the advection of streamwise momentum, while an instability induces the meandering streaks, leading to the regeneration of these streamwise vortices. This mechanism is referred as self-sustaining process. In 1997 study by Jiang, it was observed that these quasi-stream vortices are inclined in the wall, normal and span-wise direction, and they are in a staggered array. So these coherent structures are nothing but organized fluid elements of significant lifetime and scale. I thought that was worth mentioning in simpler terms. And when the Reynolds number is low, there is no scale separation, which explains the self-sustaining mechanism of self-sustaining process. But when the Reynolds number is high, at larger scales, the vortices appear in addition to these near-wall coherent vortices. So for our for this paper, the data was solicited from a website from a database by Lozano or Duran and Jimenez and this was the exact citing which they mentioned in the paper. So the entire process is a two-step process in the numerical database. So so first step is to get the to solicit the data from the database, and the second step is your scale decomposition. So coming to the methodology, uh, as mentioned earlier, to reveal the hierarchical turbulent flow structures, we investigate the data of direct numerical simulation of turbulent channel flow at frictional Reynolds number 4179. And the simulation is conducted by integrating Navier-Stokes equation for an incompressible fluid in terms of the wall normal component of the vorticity and its Laplacian. For the spatial discretization, the Fourier spectral method was used in the wall parallel directions, whereas the 7-point compact finite difference scheme was used in the wall normal direction. So at this, these were some of the related work which was done earlier, and uh, okay, let's skip this part. So coming to the scale decomposition, as we can see in the formula here, uh, here we have two in the first equation we have a low pass filter, and in the second equation also we have a low pass filter, but a band pass filter. We have a band pass filter. So I've written down notes. I will try just reading from the notes because whatever I put on the PPT was from the paper directly. So okay.
Okay.
Uh, Okay, so to understand these coherent structures, to do this, the turbulent fields are decomposed in different scales using bandpass filters. Bandpass filters basically segregate the spectral content from a fixed predefined band or wave number, which in our case is frictional Reynolds number 4719. The velocity we get after implementing bandpass filters can be used to calculate vorticities and entropy, which is the square of vorticities, and the velocity of isosurfaces can also be and we can also solicit the velocity of isosurfaces by implementing this bandpass filter. So as we can see in the formula, in the first equation is where you have a low pass filter, and in the second equation we get the velocity using bandpass filter, and this is done by subtracting the velocity field of low pass filter with another velocity field which has filtered everything from a higher value of sigma, which in our case is 2 sigma. We can also use 1 point sigma value of the bandpass of the second equation as 1.5 or 2, but we have used 2 in this paper. So once we get the difference, we have the velocity field of the coherent structure we are interested in, and we can plot isosurfaces to detect these structures. Okay, so uh, okay. So in the results part, we can observe that at the edge of boundary layers, we get eddy flow vortices, and these coherent structures and these coherent we observe that at the edge of the boundary layer we get eddy flow vortices, and these coherent structures resemble the shape of horseshoe or hairpin. Hairpin structure vortices are small structures present mostly in log regions, and here is one simulation of when the positive isosurfaces of second invariant Q of the velocity gradient tensor are visualized. Only the smallest scale vortices are captured, which are the blue objects here in the simulation. And this is because the smallest scale flow structures are relevant to quantities related to velocity gradient. But on the other hand, when we visualize the negative isosurfaces of fluctuating streamwise velocity, structures as large as the distance from the wall are captured, which are the orange objects. This is because the quantities related to velocity are predominantly determined by the largest scale structures. This example shows there is a clear scale separation between the structures associated with velocity and its gradient. So now in the slide, okay, yeah, in this slide, we have another example. Here, we have plotted the isosurfaces of the second invariant Q blue part of the velocity gradient tensor and the streamwise velocity u. So yeah, basically we have made the simulation with different values, different scale values. The A, you can see here A, B, C. A is the for 960, which is I think, yeah. So 240 is much bigger, and 60 is, I forgot that part. Okay. It is worth mentioning that these scales are normalized using volumes, and these simulations prove that these filters can extract these structures at various scales. And here we study the structure, the coherent structures more closely. So here's the average scale of the structure, and we have a formula like how they calculated the average. And so basically the black arrow indicates the center of reference frame in which the conditional average is taken. The flow is from the lower left, from left to right, and the blue arrow indicates the direction of the flow of omega, which is, and the point, the side which is it is directing is the positive omega x. The average scale is spherical, which proves that they are isotropic in nature, and the closer these structures get to the wall, the isotropy is lost. And I have some notes on this. So we can observe here, if the vertical motion of the fluid on the left side, so the green part, if the vertical motion on the left is anti-clockwise, and on the right, uh, and on the left if it is clockwise, and on the right it is anti-clockwise, then the middle will be high, and then in the middle we'll have a high speed streak. And if it is the other way around, vice versa, which is side on the left, a low speed stream, and this happens because the vertical motion will lift the velocity from the wall, and speed will reduce from there on. So this is the hierarchy we are talking about on how the large scale and small scales are shaped. So I think I'll come up with more precise words and present it again when Harsh joins later.
Yeah, Harsh is here. Anyways,
Yeah.
so the presentation was okay. I mean, it looks like you have gone through the paper, but I still
Yeah,
feel like you can gain a lot more clarity if you go through the literature a bit more.
yeah,
Uh,
right.
so now you can, if you have it, you can also present. If you have the data, if you were able to generate that data, you can also present that.
No, that part I still did do. I still have to do. I got the MATLAB code later. Then there was some confusion. Then something came up at college. Right now, actually, I'm still in college.
Uh,
I'm sitting in my professor's staff room,
okay.
and so I took the printout of this paper and I'm still reading it. I was going through it. I didn't go after that.
Yeah,
Yeah,
it's okay.
after
Anyways,
so I
so
didn't.
you should know that I'm recording these lectures and I'll be putting them on YouTube. So, I mean, so
Oh, okay.
be
Hello,
careful before
YouTube.
you show your face.
Yeah, it doesn't.
I don't know.
Okay, okay, it doesn't. I'm comfortable with that.
Yeah. Yeah. Okay. So it's okay if you have not done it yet. But you were able to get that data, right? You ran the simulations.
No, I didn't run it yet. I have to do it now in a while.
Okay. Uh, so what about you, Harsh?
I have not created a presentation or something, but I've read the paper and like I can share your screen and tell you what
Yeah,
I have
you
studied.
can present it as you are comfortable with.
Okay, is my screen visible?
Not yet. Yeah, now it is visible.
Okay. Okay, so this is a paper which basically tells us about energy cascading in a turbulent channel flow. So cascading is basically transfer of energy from large scale to small scale, basically large eddies to small eddies. Uh, and they have done it in a real space. Real space, previously all the studies were done in like spectral space, where we calculate energy with respect to some wave number. But here they have done in real space, so we calculate the energy transfer in the X, Y, and Z spatial plane. So this is the basic introduction. They have done the simulations using fully developed turbulent channel flow at Reynolds number of 4179. And this is basically all about that. Okay, so what they've done is there's something called self-sustaining process, which is the streamwise vortices induce low and high speed streaks by advection of the streamwise momentum, while an instability induces the meandering of streaks leading to the generation of stream vortices. So at low Reynolds number or low velocity, we see something of a self-sustaining process, like the vortices generate itself. But when the Reynolds number get high, some additional vortices appear. What? Okay, sorry, someone came. Uh, Large scale vortices appear in addition to this near wall coherent vortices. So basically, there are, as close to the wall, there are some vortices structures, and we'll discuss about it later. Wait, let me take out my notes. Let's talk about methods. Uh, these simulations were conducted by integrating the Navier-Stokes equation for incompressible flow. If we, in the Navier-Stokes equation, if we multiply it by velocity, we get the energy equation. That is something worth mentioning, I thought. And the Taylor length based on the Reynolds number. Why is the thickness of boundary thickness, and h is the height of the volume we are taking is at approximately zero point 0.4 is about 200. this is something of a scale decomposition. So what they've done, we get a spectrum when we do this. So we get a spectrum and mm, there's something called the low pass filter. Okay, so can I write there? Okay, so there's something like this spectrum, and so these are wave numbers, and once we apply a filter, if there's something like this, there's a low pass filter, so it will allow all the these things to pass through. Okay, no, this to pass through, this low wave number to pass through, and if we apply it, this is at sigma, at some value sigma, and if we apply it at 2 sigma, this will allow all this to pass through. And if we take a difference of them, we get a band pass filter. So basically we get this value. Okay, so this is what they've done. And there's something also called as known as vortex stretching. They have in the result section, they have told us that how vortex stretching works. And okay, I forgot to mention something that I knew.
It's okay, you can go back.
I think I don't know where it is. Okay, it is here. Yeah, okay, okay. So as mentioned in the introduction, when we visualize the positive isosurfaces of the second invariant and the velocity tensor. Okay, so this basically tells us there's something like velocity, fluctuating velocity can be differentiated in two parts, which is mean velocity plus velocity at any instant can be divided in two parts, which is mean velocity and velocity due to turbulence. Okay, so the mean velocity is generally responsible for all the large scale coherent structures. So these large scale coherent structures are in form of streaks or horseshoe vortices, and the fluctuating part, which is the turbulent velocity. The turbulent velocity is responsible for small scale structures, small scale vortices. And these scale vortices are isotropic in nature. And this is a representation that they have done for sigma. Sigma is the Gaussian filter value for 960. 960. So
Yeah,
this 9
Harsh, can you explain that decomposition again? Like the fluctuating velocity has
two
was
parts.
decomposed
One
into
is
this, right?
okay, fluctuating at any instant, there is a velocity. Like we have a signal, right?
Yeah.
So the velocity keeps changing. So what we can do is we can take a mean of the velocity
Okay.
and the mean part and the mean part goes like this. And there's some at every point, the velocity can be written as the velocity due to mean and velocity due to the fluctuating part.
Okay.
Okay, so the mean part is generally responsible for the mean of the flow, like the large eddies, or we can say the large scale coherent structures. And the
Okay. It's not necessarily true. I mean, if
okay,
your flow is statistically stationary, your mean will not change.
yes,
Okay. So what happens is your large eddies are so your fluctuating velocity, the one that you get after subtracting the mean,
yes,
it will have contributions both from the large ones and the small ones. Okay.
okay, I did not know that.
S- So if you remember the example about two superimposed sinusoidal waves that I had talked about, take
Okay,
a sine wave of one frequency,
okay,
and on top of that you add a sine wave of frequency 5 times of the earlier one.
okay,
So what you will observe is, a sine wave which rides on top of the lower frequency sine wave.
mm,
Okay, so and if you average this signal on a long enough time scales, and the time scale should be larger than the the wavelength of the largest sine wave that is there. In that case, you'll get the mean velocity, which is, you'll get a constant mean velocity. But then the fluctuating part will have contributions both from the large wavelength sine wave and the smaller wavelength sine wave.
Oh,
So the
okay, I get.
fluctuating velocity has contributions both from the large scales and the small scales. And
Oh, yeah.
these we are isolating by using filters. So if I use a filter, a large scale filter, it will filter out the uh, small wavelength sine wave, and then you'll be left with the larger wavelength sine wave, which is contributions from large structures like streaks or
Oh, okay.
something else, large
That
eddies.
that thing I did not know. I have to read that all again.
It's okay. I mean, this clarity will come when you read a lot of papers, but it's okay. The other
And
way
later,
is through discussions.
they have discussed about these surfaces, these isosurfaces, and these are at different location on these surfaces are close to wall. As we go far, they become spherical. So we can say these are isotropically distributed. But close to the wall, they are not spherical because they feel because there's wall. So wall puts like a resistive force. So that is why. But we can from these figures we can say that the small surfaces are isotropically distributed. And there is also something this. These are the large scale isosurfaces. This blue thing we see is like a streak. So when there is flow, turbulent chain flow, they form some streaks. This is a high streak, and this is a low speed streak, and high speed streak, and like close to each other, next to each other. And we can also determine how it is a high speed streak or low speed streak by this green and blue vortice, yellow vortices. They, if this is flowing clockwise and counterclockwise, these always flow in the opposite directions. So this thing tells us uh, if this is a high speed streak or low speed streak. And I guess I have to make a PPT to all get all this in like some sequence and all. I thought that it would be fine without PPT. And okay, this thing I know a little about this thing. So there are these cascades, right? Energy is flowing. So what happens is energy, large scales eddies dissipates energy, and small scale eddies gains energy, absorbs energy to keep the turbulent flow continuational. Uh, so they cannot, like if it is a very large scale eddy and a very small scale eddy, they cannot interact each other like directly. First, this have to give energy to some small scale eddy which is as comparable to this one, and then it keeps getting smaller and smaller and smaller. So this shows us what how much energy is transferred from these large scale to smaller scales, uh, like from sigma 30 to sigma 60. This much as energy is given. If we go from 30 to 120, this much is given. The difference keeps getting smaller and smaller. So that is something. And I guess that is all from me. I have to make some presentation to keep all this.
Okay, so that was what you understood from the paper. And I think you're also facing some problems with the code, right?
Yes,
You can share that as well if you want.
that like basically I wanted to know where is the code. Okay, my Visual Studio Code, I don't know how it is installed, but I'll show that to you sometime later. Okay.
Okay. I mean, you can open that file in VS Code, right?
VS Code.
You can also open it as a text file.
Yeah, I can open text file. Okay. So I don't know about all these things. Like, what are these things? Like, why it is 150 and this beta function.
Okay.
So I
Yeah,
tried to
for
change
this.
some things, and then the file was not simply running. There was
So,
some.
uh, is it just one thing you have changed or several?
No, I've changed lots of things.
Okay. And do you remember the error that you got?
My error is something related to.
The
Wait,
time scheme?
no, no, no. Yeah, it was, I guess, something related to time scheme.
Okay. Okay. Can you try running the code now?
I don't have. Okay, let me try. What? How do I run the code again? I forget that.
You have to go to the folder where your input file is.
PWT, right? I have to enter.
CD. PWD is present directory. CD is how you navigate to the directory you want. Okay. You have to go to the root folder, which is slash
Yeah, I know that, but I
mnt,
don't. Acha, MNT. Okay, okay.
uh, mnt, and then your C
Now I
drive.
know. What was ls, right? No.
Yeah, should go back to your root folder.
How do I do that?
CD slash enter. Uh, there is space between CD and slash. See what folders are here. ls.
Okay.
Okay.
Hmm.
There is mnt, but it's not. Yeah. There should be no space after your slash.
Okay.
You can use tab to autofill.
Is it like user is this? Oh, I forgot how to use Ubuntu.
It's okay. It's okay. You can.
Okay, I'll show it to you next time or
Yeah.
something.
Yeah. Also, I mean, get in touch with Mujir, and come with a come up with a comfortable time to have our next session. Uh, Possibly sometime after 31st.
Sometime after 31st. Okay.
Okay. So 31st is Tuesday. Or if you can, we can also have it on this weekend, Saturday and or Sunday. So it's better if we wrap it up early. Okay. And if you cannot do it on this weekend, then let's have it after 31st.
Okay.
Okay.
Yeah, I'll make a presentation till now. Till then.
Okay.